Hello and welcome back to the 2019 Virtual Summit on AgTech. It's Matt and Rachel here live from Tuck again, kicking things off for day two. We are so excited to be back. Yesterday was an awesome day full of some really interesting content, talks, and panels. We're switching gears a little bit today, and we're going to be talking all about data, precision agriculture, and a lot about satellites and geospatial data. And so in order to kick that off, we're going to introduce Mark Johnson.
Yeah, a few points before we dive into our first speaker. If you have any questions, please use the Ask a Question again, that functionality, and hopefully we can make this very iterative and collaborative. But
Uh-oh. Looks like we lost Matt. Am I still here?
Hi.
Hello, everybody. We're back.
We're back. The tech issue, lots of opportunity for improvement in ag tech and otherwise. But to introduce Mark, we're so happy that you're here. Thank you for joining us. Mark, as you know, you are the CEO and co-founder of Descartes Labs. Mark served as CEO of the AI-driven news service Zeit before founding Descartes, which he sold to CNN 5 months after the company launched. He has spent the past decade working in machine learning and big data, taking 3 search startups to successful exits. So Mark, feel free to elaborate and edit, but would love to hear from you. Thank you so much.
Okay, well, thank you everybody for joining. I really think this virtual conference thing is really cool, so I appreciate everybody being online. I'll stop regularly for questions. Today, thanks for the introduction. I'm going to tell you about my latest company, Descartes Labs, and how we are going to try to understand the planet thanks to the enormous amount of sensor data coming online. So I thought I'd start off with just reminding us that it hasn't been that long since we got our first picture of the Earth. So Stuart Brand asked in 1966 why we haven't seen a picture, and this famous blue dot picture came out in 1968. And think about this. This is the first time that humanity had a bird's eye view of the entire planet. Since then, we've put up thousands of satellites to try to understand the Earth better. And the challenge with this data is the Earth is really big. So 150 million square kilometers of landmass and more in the ocean. This is sort of a picture from the 90s of kind of what the Earth looks like from a satellite with relatively low resolution. The challenge with this data is how do you bring it all together in one place and make sense of it? So what you need is there's a lot of clouds on the Earth. You need to get rid of the clouds. You need a ton of imagery. So again, 150 million square kilometers means that you need multiple satellites taking multiple pictures in order to get a full view of the Earth. Indeed, so this is something that we created. This is basically, you'll notice something's funky with this picture. There's not a cloud in the sky. And the way we did this is we took years of imagery and found the best possible pixel for each of those, normalized them against each other, and created this sort of false view of the Earth, right? This completely cloud-free view of the Earth. And again, this is challenging. So we had to use 4 years of imagery here. So hundreds of terabytes of data went into making a map like this. That what's great about it is because there's nothing obscured by clouds, you could search for objects all over the globe. But another thing that's really neat about satellite imagery is it's not just the red, green, and blue that your eyes are used to seeing. There's a whole spectrum of bands that come off of satellites that tell us a lot about what's going on. So this is the visible band, red, green, and blue. This is near infrared. So basically, if you could see just slightly beyond red, you would have a view like this. And it's a really useful data set for vegetation, so very relevant to the conversations we'll be having in understanding how healthy plants are. So plants are like little factories, and they absorb and reflect light. And by looking at that light, you can tell how healthy they are from space. There's even sort of different modalities of sensors. So this is actually what's called synthetic aperture radar. So if you think about how a regular satellite works, the sun bounces off of the Earth and is picked up by the satellite, much like a camera works. This is actually an active sensor that shoots down a beam of radar onto the planet, and then it bounces back. The satellite picks it up, and it gives you sort of an idea of what's changing through time. It's almost like seeing like a bat. So we have all these different types of data sets. And this is neat. This is an image from a brand new sensor that just went up with the European Space Agency called Sentinel-5P. And what you're looking at here is greenhouse gases. So this sensor is tuned to look at the spectral signature of various greenhouse gases. In this case, this is nitrous dioxide, which is produced by things burning. And you'll notice a few really interesting things here. If you look over the Atlantic, you can see sort of shipping and airline paths. If you really squint, you can sort of see there's sort of a shipping path that goes all the way from Spain through the Mediterranean, through the Suez, down to India, and then sort of all the way up into China, obviously major shipping route. So what's amazing about these satellites is they really allow us to better understand the planet. And I can't imagine a more critical time to be gathering all this data and thinking about how to build a digital twin of the planet so we can be better stewards of our natural resources. So that's sort of like a brief sort of, I wanted to give you some context for how interesting this data is about the planet, and sort of why we chose this as our first data set. But now I'm going to take it a step back and try to explain why this isn't just important for the health of the planet, but rather why I think that we're hitting on something that every company will ultimately need. And then I'll bring it back to Descartes Labs and show you some examples. So, we've lived through, well, I've lived through 3 major technology revolutions: PC, internet, mobile. And these fundamentally changed how business was done. Media will never be the same. Assets were digitized. So DVDs turned into Netflix, killed Blockbuster. Books turned into Kindles, CDs turned into iTunes and Spotify's and Pandora's. And that changed the distribution model and fundamentally changed the business model. And these, of course, are decade-long processes. I'm sure if you were lucky enough to see the early days of the internet, you would be shocked if I would tell you 20 years later that we would be running a virtual conference through your web browser, given that it was just a bunch of text and pictures on the page. But these really changed the way the world worked. We're sitting on the cusp of another revolution, and it's really just starting. And there's 2 components to this. One is the massive amount of data that's coming online. So we, of course, look at a lot of satellite data, but there's weather data. Every combine, tractor, truck, barge, boat has a sensor on it. Most companies are outfitting their plants with sensors. There's cell phone data, all sorts of things that you want to pull into one place, and then artificial intelligence to make sense of it. But I think unlike the previous revolutions, we're lucky that there are actually a few companies that have already done this and can kind of show us the way. So the way I look at each of these companies is that they're like massive data refineries. So they pull in a certain type of data set, and they use that to make predictions or recommendations about the world. So Amazon, of course, has an enormous amount of user purchase history, and they recommend what you want to buy. Facebook predicts what you want to read. Google takes the web and predicts what you're searching for. Then Netflix, very interestingly, they have an incredible data set on what people watch. And not only did they use this to create an incredible recommendation engine, but at some point in their history, they realized that why recommend someone else's content when you can recommend their own content? So new businesses can pop up because of these data refineries. So what we have built is a data refinery focused on commodity supply chains. So agriculture, metals and mining, oil and gas. So these large natural resources in the world. And what we do with this data refinery is we look for changes in the world using these sensors, and they make predictions about future states. And we think that the components of this are a massive data store. We have about 15 petabytes of data in the archive right now, and we download somewhere between 10 and 20 terabytes of new data every day. So there's models that run on top of this data, so trying to make sense out of it. The raw data itself is just data, and you need to make models to give it some semantic quality, to give it some sense of what's going on in the world. And really importantly at Descartes Labs is we focused on making this scalable. Because we tackled such a big problem, we needed to create supercomputing level power within the cloud, so we can ingest a lot of data, process a lot of data, and build models at global scale. And this is really, really important. So one of the challenges of machine learning is how do you scale it up? This where we train a model in a small area, test in a slightly larger area, and then run it at the country or world level. And the reason this is important is that the way Descartes Labs looks at the world, we're not looking at necessarily sort of the individual farmer or the individual farm. We're trying to understand things like supply and demand at the country level. So this kind of supercomputing capability, this kind of HPC or high performance computing capability is absolutely critical if you want to understand the entire planet. And why is this important to supply chains? The challenge for a lot of the companies operating in the agricultural supply chain, so this is, think of your seed and chemical companies, your equipment manufacturers, your grain traders. These are enormous companies with massive, massive supply chains. And the challenge for them is that historically, one of their advantages in the market is because of their access to their assets across their network. And this gives them information. So if I have a grain elevator in Peoria, Illinois, I can call up the grain elevator manager there and understanding what's happening in Peoria. If you have satellites taking pictures of the planet every day, suddenly information that might have used to be proprietary to just you is now known by the entire supply chain. So the question for these companies is, how do they use these new alternative data sources, combine them with their internal data sources, and actually get an edge on their competition rather than just lose this edge because all this information is available in the market. So this is how we work with our customers. So with our data refinery, there's two primary ways that our large customers come to us. One is with a problem with their data. So they often have large data sets. One of our jokes is that companies talk about data lakes, but often they're data swamps. So we can organize that data and make some sense of it and combine that with external data sources. And the models on top of it, either we can build them. So we have a team of applied scientists internally. So these are sort of PhD geographers and physicists that can build models for you, or we offer API access to the platform. So that's sort of how we think about the world. We think that every organization ultimately will be transformed by this idea of a data refinery, that this is like the next generation of enterprise software. So the first generation, digitized internal operation, that's great. That means your finance, your HR, your supply chain internally are online. But what we hope to do is help customers better understand how they operate in a larger environment. So how did we get here? So about 4.5 years ago, I met a team from Los Alamos National Laboratory, and they had been working on deep learning artificial intelligence for sensor data. So Los Alamos National Laboratory, of course, is the steward of the National Nuclear Stockpile. It works on many, many critical problems for the government. So this is sort of a proven technology that we were able to find. And this was about analyzing sensor data at scale. So once we spun out of Los Alamos, we wanted to find a really large, complex scientific data set to go test some of these theories. So to test whether we could run this at scale, to test whether we could commercialize it, we decided to look at satellite data for a few reasons. One is there's just an enormous amount of it. Landsat actually took its, which is a publicly available US satellite. There's been 7 that have gone up. And it has a 45-year history. So it started in 1972. So we have continuous pictures of the globe. There's lots of new satellites going up. There's lots of interest in commercial space. And one of our observations was that when there's a huge investment in hardware that's going to produce a lot of data, there ought to be a commensurate investment in software because you need the software to interpret that underlying data. So this is where we started off. And we said, well, what can you do with it? Interestingly, at Los Alamos, one of the projects they had worked on was looking at illicit crops in Afghanistan as a proxy to how much money the Taliban was getting effectively. And we saw this question of global agriculture as a really interesting problem. I mean, frankly, like I didn't know a lot about agriculture or satellites when I first started this company. And it was astonishing to me that even though we know how much grain is growing in the US, the USDA does a pretty darn good job of this. Globally, there's a lot of questions about how much food is being grown where. So treating this as sort of a large-scale search problem over the globe was how we kicked off the company. So about 9 months in, we challenged ourselves during those first 9 months to come up with something that would actually be useful. I mean, after all, think about it. We were spinning out of a national lab, so we wanted to prove that we could go. So we looked at the USDA, and the USDA, as probably most people in this conference know, releases forecasts for crop production during the growing season. Their first one is typically mid-August. And what we decided to do is see if we could build a corn forecast that was as good as the USDA's. We were able to, within 9 months, using many satellites and tons of weather data and many hours, we were able to come up with a model that had 3 qualities that were better than the USDA. First, it was more frequent. So the USDA, the way they're so good at forecasting corn is they go out to fields, they talk to farmers, they basically survey and pull out, say, tens of thousands of data points. We see every farm every day, so it means that we can do a daily updated model based on crop health. The second is that it's more accurate. So we can go look at historical satellite imagery and figure out what we would have said in those years. So we can show you a model with some historical backtest. The third is that because we have so many data points, we're able to do in-season predictions at the county level. And this might not be important if you're trading corn in futures markets, but certainly really important for spot pricing as you have an asset in a county or something. So when we released this, there was an article on Bloomberg, and we moved the price of corn 3%. It bounced back, but as you can imagine, this is a point where the market really took notice of what had happened here. And if you think about it, part of like what we showed the market was that we can combine different data sets and get better models. So once we built this, we started working with customers and showing them that if they combined their data with our data, we could get an even better model than we could independently, because customers often knew things that we didn't know. One of the companies that noticed this was Cargill. So Cargill, of course, the largely privately held company in the US, although I guess they're neck to neck with Coke. So we ended up working with the grain trading division there, Coke Agricultural Services, Cargill Agricultural Services. And that's the division that owns all of the grain elevators and moves physical grain all around the world. So we help them better understand global supply and demand so they can better trade grain. And they also have an investment in the company. So we're helping them kind of sort of undergo this digital transformation, kind of pulling in these alternative data sets and combining it with Cargill data to help them better trade. We also do a lot of work with DARPA. As I mentioned earlier, I was shocked to learn that we don't know how much food is growing on the planet. DARPA specifically asked us a few years ago to look at the Middle East and North Africa. So as you can imagine, you can do a crop tour in Iowa. You can just walk around to the fields. It's harder to do that in Libya. So we look everywhere from Morocco to Iran, so 33 different countries. And we try to get a sense of where there might be food disruption. So if there's some crop failure due to pests or due to droughts, we can pinpoint those. And the idea is to be able to send in humanitarian aid to prevent political unrest, so we don't have to actually send in the military later. DARPA was really impressed with this, and we are actually now building for them sort of the next generation of geospatial cloud analytics. So this is a project to try to bring in multiple sources of data and build models on top of it. We also can, I'll just give you a few more examples and then I'll wrap up for some questions. But really interesting thing that you can do. So of course, 80% of the surface area of the Earth is oceans. At any point, there is an enormous amount of value on the oceans: oil, iron ore, gold, crops. So we can track this around the globe. And this is really important. So Of course, we help customers understand supply and demand factors, but once you understand how much supply there is somewhere, the challenge is getting that to a place of high demand. And in almost every case in commodities, the place the commodity is created is not the place where it's consumed. So, a lot of iron ore that goes into China, for example, comes out of Western Australia where no one lives. So, efficiently getting those commodities from the places where they're being produced to the places where there's the most demand really helps our customers to optimize their supply chains. We also do some really neat stuff in terms of a better understanding climate change issues and understanding. Forest fires are really near and dear to our heart. You can see a picture here of New Mexico and a bit of Texas. We never left, after we left the labs, we never left New Mexico. So the company, I don't know if I mentioned this, is headquartered in Santa Fe, New Mexico. And it's a high desert. So we're to 7,000 feet, right on the edge of a national forest, sort of the southern tip of the Rockies. And last year was a really bad drought year. So we decided to build a fire detector to better understand forest fires. What's neat about this is that it uses a satellite that takes a picture of the entire continental United States every 5 minutes. And within 4 minutes of that picture being taken, it's in our system. And there are interesting bands on that satellite that go beyond the visual. One of them is a thermal band. And that thermal band, we can see anomalies that correlate to fires. And this is still a very ambitious project, and the technology is not quite there yet. But we have been able to show, in looking at historical data, historical fires that have popped up, we have been able to detect fires in remote areas before they were reported. And as you can imagine, with forest fires, absolutely every minute counts. So the sooner the authorities are alerted to it, the better. This has lots of implications, not just in our natural resource management in our forests, but also for insurance purposes and whatnot. This is really exciting, and this really gives me hope for better understanding the planet and better being able to understand and respond to natural disasters. Another thing that we can do with this technology is understand sort of global assets. So finding things on the ground, all the economic infrastructure that runs the world. We did a really neat post, a blog post a few weeks ago, looking at energy infrastructure in Texas. So not just looking at oil wells and oil storage, but also looking at all the solar panels going up, looking at all the windmills that are popping up too. We found this small area in Texas where it's just incredible. It's like the energy production capital of the world. You've got huge amounts of wind, huge amounts of solar, huge amounts of oil and gas production. And by watching these factors on the planet and watching them through time, we can better understand that infrastructure and plan around it. So one of the exciting things that we're starting to build in the system is sort of understanding the various objects and that computer vision can find, understanding how humans are changing the planet. Another really interesting and exciting satellite I mentioned earlier is the Sentinel-5P that looks at greenhouse gas emissions. And the idea here is to really be able to measure these emissions and associate them with where the emissions are coming from. So if you look at, for example, the Permian Basin, the largest oil producer in the US now, partially in New Mexico, there's a big old methane cloud over it because of all the methane leakage from the fracking process. We can start to track that and pinpoint the source and allow companies to operate more responsibly. To me, this is incredibly exciting. If you look at companies in the commodity supply chain, they often sort of escape the effects of their externalities. So you can't really quantify them right now because you just can't see this stuff. But as all these sensors go online and allow us to start quantifying those externalities, we can start helping these companies sort of reduce them and operate far more efficiently. So to me, this is a great example of a way to combat climate change with a market-based approach. So really trying to solve problems for companies and giving them the opportunity to fix environmental problems that they might have. So I'll end here and then I'll take some questions. This is pretty exciting. we're not just looking at supply chains. We're really thinking about this as understanding the globe and understanding some of the biggest problems and challenges that we'll have in the 20th century. Climate change is here, and everybody is going to have to deal with this. We have to reduce carbon emissions, and not only can we help companies operate far more efficiently, but we can also help them to operate far more responsibly. And to me, that really gives me hope about the future. That I know there's a lot of chatter about AI and data right now and all the negative things that might be done with it. But I always like to remind people there's enormous amount of positivity that can come out of taking these large data sets, refining them, building models on top of them to help us understand the world. So thank you very, very much.
Awesome. Thanks so much, Mark. This was super interesting. As mentioned, let's go to some questions. Number one from Claire. Perhaps naive, sorry, but how does, say, a Montana wheat pulse farmer get data about his own cropland? Does the farmer have to buy data about his farm from Cargill? Really good question.
That's a great question. So we took a very particular view of the market. When I started the company, kind of did an overview of AgTech and kind of looked at what the market looked like. And there were plenty of companies doing some kind of farm management software, helping farmers to better manage their inputs, better market their grain. We felt like there was a pretty saturated market. But what no one seemed to be looking at was sort of global scale factors, so large scale factors, kind of the top of the supply chain. So not just looking at an individual field and the output of that field, but rather looking at the output of a county, a state, a country, or the entire globe. So Descartes Labs really takes this sort of top-down view, trying to understand global supply and demand factors, sort of not just for an individual farmer. One of the reasons for this also is that this is really important to understand in AI. You've got to match your problems to the data sets that you actually have. And the reality is that satellite data is not high definition video from space. You sort of get these occasional grainy pictures at relatively low resolution. And that's a great data set if you're looking at crop production at a large level, but not really useful if you're just looking at the farm level. One of the consistent problems is clouds. If you have a satellite taking a shot every 5 days in August in Iowa, your chances of it being cloudy over 50%. So, it takes a while before you get a shot of that field. So thank you, Claire.
Another question. Just going down the order of votes. In an era of global warming and concerns about dead zones being created, can you use your data combined with weather pattern data to help farms and perhaps government agencies to understand what crops will be optimal on their lands?
It's a great question, Jim. Yeah, I think that one of the things that we believe is that by making this data accessible in the market, everybody can operate much more efficiently. So one of the things that we can do is help farmers to understand not just what's happening locally. So oftentimes when a farmer makes a planting decision right now, it's really like sort of chatter in the county to figure out what to plant. We can give them a much more global view. And I think one of the things that's really exciting in the developing world is really helping crop management. So really helping farmers to figure out what to plant, what's optimal in their area, and then distribution. So again, looking at even a local scale in places like Central Africa, and trying to go from effectively sort of small farms into smaller areas. So these sort of regional areas for distribution. There's a lot of potential there. One of the challenges with global grain production is that we have plenty of food for the planet. The real challenge is in distribution. And I think understanding these global supply and demand factors will help at the local level, helping farmers to figure out what to plant, but also moving those areas of supply to areas of demand.
Great.
Awesome.
I think we do have time for our last question, which is from Kirk. Is there an online index of publicly available satellite imagery, and what might it be useful for?
It's a great question. So no, unfortunately, there's not a really good index. We should probably put that somewhere. That'd be a useful thing for us to put on our website somewhere. just for everybody. NASA has a series of incredible satellites. So the Landsat, there's 7 and 8 operating. Those are basically weekly, together they're weekly pictures at about 30-meter resolution. There's a great set. There's 2 satellites, Aqua and Terra, in the MODIS program. Those allow for daily monitoring, but it's sort of the 250-meter to 1 kilometer resolution. I told you about GOES, which takes pictures of the continental United States every 5 minutes, at like about a kilometer resolution or more. And then there's a whole series of incredible satellites that have been picked up by the European Space Agency in their sort of creepily named but incredible Sentinel program. So everything from radar to the next generation of Landsat to the next generation of MODIS. So there's a lot of publicly available data out there. In fact, this company was built on the incredible archives that we've been building up for decades. And I think these are basically most that NASA ever did, and that when they first put up Landsat 1 in 1972, there wasn't enough storage space on the entire planet to store the images coming down, so they went on film. But they were really smart to do that because now we have decades of great data. So yeah, I really encourage, if anybody is an expert in Python and wants to explore all the data in the archive, please get in touch with me and I'll make sure you get access.
Awesome. I think that's it. Matt, any other?
No, just Mark, thank you so much. We really appreciate it. I guess the only joke of this conference is that our abbreviation is VSAT, which has no reference to a satellite. But we are so excited to have heard from you and all the work you're doing and have a lot of satellite conversations today. So super interesting and fascinating. So thanks.
Maybe the output of this conference should be putting up a satellite. We can help you with that.
Hey, there we go. We might have to talk about that. We'll ask Jim if he can help us sponsor it.
Fantastic.
Great. Well, thanks. Have a good rest of your day. And everyone who's on, stay tuned. We're going to close for 10 or 15, come back on with another panel with quite a few interesting speakers. So thanks, Mark. We appreciate it and hope to hear from you soon.
Thanks, everyone.
Bye.
Bye-bye.